All right, so let's go ahead and take a look at how to obtain these transfer functions we've been talking about. When we actually have a circuit in front of us, how do we obtain the transfer function for that circuit? And in this case, I'm kind of only showing the output voltage and the input voltage, so it would be implied that the transfer function that we're interested in would be a voltage gain, okay, V out over Vs in this case. And so let's take a look at how to go about obtaining these transfer functions. So step one is obtain the frequency domain equivalent of the circuit. Okay, so my circuit here is given in the time domain, right? I have an input Vs of t, I have an output V out of t. I'm looking at a resistance value and a capacitance value, right? Well, if I want to transfer that over to the frequency domain, or the phasor domain, sometimes it's called, I need to draw the equivalent phasors for Vs and Vo, right? V, the input and the output. So in this case, it's just going to be Vs, capital Vs for the input, capital Vo for the output. Those are going to be just the variable names that we use for our phasors. And then, of course, we need to convert impedances, resistances. So R, of course, goes to, or I guess I should write it this way. The impedance of a resistor is just the resistance itself. We know that the impedance of an inductor is J omega L. And we know that the impedance of a capacitor is 1 over J omega C. Okay, so that's a little refresher. Just put those here. And so, of course, we took this C and converted that to a 1 over J omega C. We took this R and converted that to an R. Nothing changes for the R. And so once the circuit is in the frequency domain, of course, we're ready to move on to step two. And step two is very broad, and I wish it were more systematic, but it just isn't. And it's basically everything we've learned up to this point from module 1 of this class and everything from EE220. Use any circuit techniques that you must to obtain the ratio of interest. So you basically need to write the equations and expressions that you know you can use to solve these circuits, and you need to extract V out over Vs, right? The voltage gain in this case is what we're interested in. So you need to basically solve this circuit in some way that's going to give you an expression for V out over Vs, right? That is how we obtain the transfer function. And so it's not super systematic, but of course each circuit has its own methods that work well for it. So this circuit happens to have methods that work well for it. It looks just like a voltage divider. And so let's go right on to the next slide and we'll go ahead and solve this one. So let me redraw the circuit one more time, because I do like to draw it as just two impedances, just like this, so that we can really see that the voltage I'm interested in, VO, is really just the output voltage of a voltage divider created with impedance R and impedance 1 over J omega C, right? And so just the same way that we would typically write our expression for V out, we would just say V out is equal to V in times Z2 over Z1 plus Z2. We're going to do the same thing. It's going to be equal to V in, or in this case, it's going to be equal to Vs times the impedance of the second element, which is my capacitor. So I'll write 1 over J omega C, right? That's my Z2, divided by R, right? Plus 1 over J omega C. Okay, now this looks pretty ugly, but we can make it nicer if we multiply the top and the bottom by J omega C. Okay, so that doesn't do anything to our expression. We're basically multiplying by 1. But we can get rid of the fractions by multiplying the top and the bottom by J omega C. Okay, so V out is equal to Vs times the top is just going to go to 1. And then the the denominator, the first term is going to go to J omega RC plus 1. Okay, that's not so bad. And so now what do we have to do to get the voltage gain, which is V out over Vs? We just need to divide both sides by Vs. So finally, we just get V out over Vs, or the transfer function for this circuit, is going to be equal to 1 over 1 plus J omega RC. Not bad at all. Okay, so that is our transfer function for this circuit. So let me just go ahead and move some of this stuff around so that it doesn't look so messy. All right, and so that's our transfer function. So we figured out how to obtain the transfer function for this circuit, and that's pretty straightforward. Again, remember that when we looked at this slide back here, it said that our transfer function would be some function of omega, or the frequency, right? H of omega. It's going to be some ratio of the output to the input, and we're going to end up with some function of omega. Well, of course, if we look at this expression, it is a function of omega. It's also a function of R and C, which are constant values. But again, remember what I said at the beginning when we did the course introduction is that in this module, we're going to be looking at frequency response, which is how does my circuit respond as I vary the frequency. And so this right here, this expression right here is going to tell me what happens to the voltage gain, right, as I vary omega, right? If I change the value of this omega here, this expression is going to change. So what we look at when we obtain the transfer function is how does the circuit behave, or how does some particular ratio that I'm interested in this case, the voltage gain, what happens to that ratio when I vary omega, or when I vary F, if I vary my frequency. Again, we could rewrite this expression in terms of F. If we just let omega equal 2 pi F, then this expression would become, could write it one more time, 1 over 1 plus j 2 pi F RC, and that would be the exact same expression, except I've just replaced omega with 2 pi F. And so now this function, this transfer function, is a function of F instead of a function of omega. Okay, so I'm gonna go ahead and end this video right here, and then I believe in the next video I'm gonna do another example, but using an RL circuit, just kind of drive the points home. Okay, so let me end this video right here.